Hi, good morning, good afternoon, and good evening to everyone joining us from around the world. I'm Barb Riegel, Senior Product Marketing Manager for Keysight's Network Test and Security Portfolio. I'll be your host for today's session, Simplify 1.6T Ethernet Testing, a new way to validate interconnects, presented by Keysight Technologies. We're glad to have you join us. Before we begin, just a quick reminder that this session is being recorded and it will be available for on-demand viewing. If you have any questions during the presentation, please submit them in the Q&A panel at any time. In today's webinar, we'll explore how 1.6T Ethernet is moving from concept to deployment and why validating the performance of high-speed network interconnects is more critical than ever. You'll learn how to tackle some of the challenges that are found with traditional approaches and by using new tools and methods that can help automate, simplify, and accelerate your test cycle. Leading today's session is Charles Seifert, Senior Product Manager for Keysight's hardware platforms. And Charles is responsible for Ethernet data communication, test and measurement hardware systems. He has a particular focus around high-speed 1.6T Ethernet and beyond. He's working on things coming down the pike at much higher speeds as well. And Charles has 25 years of experience, having worked in the industry since 2000. Angela Grigoria, software architect with Keysight's Network Test and Security business, will also join us a bit later, and she'll show us a brief demonstration of the Interconnect test system software and the first of its kind patented Interconnect library, which you'll hear more about. Angela is the development lead for the Interconnect software and has 14 years experience designing, developing, and architecting several other leading network test products. And she has a focus on making applications easy to automate. Okay, at this time, I'm going to turn it over to you, Charles. Thank you for leading our session today. The floor is yours.
Thank you, Barb, for the introduction. Welcome, everyone, to our presentation on Simplify 1.6 terabit Ethernet testing, a new way to validate interconnects. Today, we're going to focus on the validation of the performance of high-speed interconnects. We'll review industry drivers and challenges, critical measurements, solutions available today. We'll have a nice demonstration of a new software tool that we have for interconnect validation. And we will then take a little look ahead at some of Keysight's upcoming error performance validation portfolios. And then there'll be some time set aside for Q&A and closing remarks. The acceleration of higher speed adoption. I know that most of us here are very familiar with this topic. However, a recent report from the 650 group really demonstrates what is going on with our higher speed technologies and the rate of adoption. If we take a look at the gold and gray graphs here, we can see that the adoption timeline is much faster than our previous speeds of, for example, 800 gig E, 400 gig E, and 100 gig E, and that the ramp up is incredible. Inside a period of 1 year, we are reaching revenue streams that took anywhere from 3 to 4.5 years in the past with slower speeds. So we're all feeling the pressure of the higher rate of adoption of these new technologies, which means our projects and our capabilities have to be developed in record timeframes, and we're all feeling that pressure. Everywhere we look, no matter what type of interconnect for high-speed Ethernet that we take a view of, we can see growth. This is a chart from another 650 report on active electrical cables that shows silicon shipments. And I think where the purple line is shows where we are today. And if you can see, this amount of shipments that's projected to start in 2026 has a huge growth curve. These are very high growth marketplaces. And of course, as we ship more of these, the amount of testing that we're going to do is increasing. In fact, that test burden is already increased. And this is just another example of another interconnect high growth market. There is also new technologies accelerating interconnect performance and innovation. Advances in NPO and CPO network equipment. There has been tremendous efforts put in to increase reliability and connectivity or connector designs, which will make these solutions of the near future more palatable to the high volume end users. There's also Ethernet for scale-up networking. There's a new Open Compute specification for scale-up networking that recently came out, and it focuses on lower latency and at high bandwidth connectivity. We have Credo Semiconductor has introduced something called zero flap optics, which is an advancement in chip design and capabilities that could increase reliability of transceivers and provide system hardening, telemetry, and remote management, making all of those things easier so that we can talk to lots of optics that are installed into a large data center and get that information much more easily, and also get information revolving around potential for failure or prediction of failure. There's also standards being developed for liquid-cooled optical transceivers, in addition to switches and servers, which are already there today. However, the transceivers themselves will now become liquid-cooled as we move into 1.6 terabit, into 3.2 terabit, as we move towards 448 gigabit per second electrical lane host interfaces coming up soon. And then we see very high density AI network racks of different configurations. There's a lot to look at here, but basically today, right now, there are backplanes that are thousands of copper cables that are disaggregated that create the backplane for an AI network rack. And all of these cables in their various states of assembly have to be tested. And there are new unique solutions for doing that. So there's a tremendous amount of effort going into increasing the quality of interconnects, and a lot of new technology coming into the picture. For example, PCIe, typically used in copper cables, but with the newer versions of PCIe like PCIe 6.4, 7.0, are going to be faster per lane, and they will eventually move from copper interconnects over PCIe to optical connections, another new trend that will help us speed up, increase the bandwidth and speed up communications. And then, of course, we have the 448 gigabit electrical lane host interfaces, and that is coming more than likely within the next 2 years, and will be, again, on that adoption curve that we showed earlier. Now, as all of these technology influences and all of these faster lane speeds come to fruition in the marketplace and in the ecosystem, there are many challenges for high-speed interconnect validation. And today we're going to review those at a fairly high level, but enough to communicate where we see the challenges today. The number one question: do your interconnects meet your customers' performance expectations? That's the number one question. I also believe it's among one of the number one problems. Now, what we have learned, and we have tested many, many different kinds of interconnects at high speed at Keysight for quite a number of years now. We have learned that these interconnects require error performance validation in order to show the end users that are managing these AI and data center networks, that these interconnects can meet their performance and reliability requirements, performance that we have never been asked to meet in the past are current and present today from those end users. Many of us know this that are on this webinar, and if you didn't, you're about to know it if you get into that environment. Now, what we're going to talk about today is essentially relatively new principles for interconnect validation. One of the things that we have to get beyond is, in the past, we would test our PAM4 interconnects with BER, bit error rate testing, bit error ratio testing. And then we would say, well, if we've tested these lanes at the electrical layer or the optical layer, that's good enough to predict system level performance if we met a specific industry standard specification. And actually, we have learned that testing with BER alone, while still mandatory and absolutely required, it's not enough. Now, what the problem is, as I mentioned earlier, interconnects in production networks must outperform industry standards specifications by several magnitudes of performance. It's been our experience that many end users want to see performance well beyond the acceptable levels of performance that have been indicated in our most popular standards, IEEE and OIF. And so therefore, our performance has to be measured directly and over some long period of time. And so what we'll talk about today is how critical it is to test interconnects, not only as standalone, which we've been doing for a very long time, but also interoperating with network equipment and how that affects our performance. And then something I like to call system level interconnect performance testing is required, especially in long duration tests, in order to prove reliability and long-term performance. And I say system level because we need to test these interconnects exactly as they're going to be used in the production network where they're intended to be installed. Now, what are the critical measurements for error performance validation, and why do they matter? As I mentioned earlier, measuring BER at the physical electrical layer and in the optical path is an absolute requirement. It's mandatory. So all of the work that we do with physical layer 1 equipment, where we do things like electrical conformance, electrical compliance, where we might do stress testing, design validation, signal integrity analysis, impairment and stress testing, all of those things still must be done. There is no exception to that. However, recently, with the introduction of PAM4 interconnects, we have to measure BER at the digital layer across all lanes simultaneously. This is the beginning of the system level testing, where we're measuring all 8 lanes of transmit and receive together. And how is it performing as if it was in a real network? Also, a very important part of long-term reliability is the verification of effect symbol error correction performance. Another is to validate the very complicated CMIS programming on the interconnect. Today, interconnects support anywhere from 1 to 5, 6, 7, 8, 9 different configurations of operation. All those configurations, all those different Ethernet speeds or gigabits per second speeds for DWDM, all of those have to be tested. So in the past, we would test an interconnect for 1 speed. Today, we need to test that interconnect for multiple speeds. So this increases the amount of work we need to do. And then we also want to be able to show our customers and persons of interest that our interconnect can perform at the network layer using at least layer 2 Ethernet frames at line rate under stressful traffic transmit and receive conditions that shows the performance under real world conditions with real world traffic. So this becomes even more important than it used to be. In the past, transceivers and interconnects were tested without any Ethernet traffic passing over them. Today, it's becoming nearly mandatory. And then we want to take our interconnects and then we want to do, as we mentioned, system level performance, looking at the BER, looking at the forward error correction performance, looking at the layer 2 performance under stress. But also, when we take these interconnects and we connect them to different vendors, multi-vendor interoperability, when we do that, we want to see what the performance is when we are working with 4 or 5 different PHY chip, SerDes chip vendors. Maybe it's a switch ASIC vendors. Depending upon what kind of equipment we're working with, we can have multiple vendors supplying equipment into a single facility, and all of the interoperability still it has to be tested because it can be different and levels of performance can change between the different vendors in these complex systems. And then there are times when we would want to take our interconnects and install them in a known good switch, for example, or a router or a server, and run a benchmark performance test and really stress test them in traditional ways, but yet include and review the performance of the interconnect itself. Okay, so to summarize what we talked about, there's a bit of a process. That process starts with evaluating BER on all lanes simultaneously at the system level, taking those performance measurements, comparing the performance of one lane to another, or the cumulative performance of all the lanes. And then we look for lane crosstalk problems. And yes, you might say, well, yes, I do that on my physical layer equipment. Of course, you have to do that. However, when we get to the digital layer, the error performance validation layer, we also look for this. So we have to have test systems that can test on a single lane or a group of lanes or all lanes. And they have to be flexible enough to do that. And we have to have systems that will help us determine the difference between lanes and make it easy for us to compare them to see what's going on when we're running all lanes simultaneously or some group of lanes. And then we want to look at the forward error correction performance on all the lanes. What is the prefect BER and other measurements we'll review today? Then we also want to do our bursty error detection and counts, because this is the culprit. The bursty errors can occur on a link at any given moment. It's unpredictable and it's not time related. It could be temperature and time. It could be a certain stressful traffic pattern. It could be a certain stressful condition on the interconnect that might produce bursty errors. It might be mechanisms involving the DSPs that happen to be in the transceiver or on the interconnect. It can be a combination of the host and the DSP. It can be a combination of two hosts communicating where there's no DSPs in between but two hosts and a link. Depending on our condition, our topology, we still need to look for bursty errors. And when we find them, we have to count them and see what their impact is on our link reliability and our effect symbol error correction performance. And then we have to do interconnect system reliability under stress, under temperature, over temperature ranges, with stressful traffic, both BER, PRBSQ patterns, forward error correction, line rates, scrambled idle traffic, layer 2 Ethernet traffic that in certain ways can be injected that are very stressful on the device. All of that has to be looked at system reliability. And then network deployment readiness, which is basically doing all of these other steps first in validation, and then moving to the network deployment aspect, which is we've done some multi-level, multi-vendor interoperability testing, and we can confirm our performance across by interconnecting to different vendors. So this process is very important to go through, and today it includes all of our physical layer processes we've been doing for years and years, and now it's a whole lot of digital error performance validation process. So let's start with BER on all lanes simultaneously. We can select whatever PRBS pattern, PRBSQ pattern we would like to transmit, and when we do that, we can see the BER of each lane when it's received and error detected. Now, we also want to do lane crosstalk detection, as I mentioned, which is comparing lanes to one another. So your tool needs to be able to do that. And when you're using forward error correction, scrambled idle traffic, we want to look at our prefect BER, our prefect BER value, right? Now, the prefect BER value makes it very easy to compare lanes with FEC scrambled idle traffic. Then we move to our FEC symbol error distribution performance. As we mentioned, prefect BER per lane, maximum symbol error is found per code word per lane. That's an interesting number. And FEC symbol error correction and distribution. So we bin the symbol error values that we find from no errors to 1, 2, 3, 4, all the way to 15 individually. And then, of course, we look for no uncorrectable code words, no uncorrectable events, and we look for frame loss ratio equal to 0, which basically means we did not have any uncorrectable code words and we didn't have any bursty errors that would have caused those uncorrectable code words. And remember, with forward error correction, if we lose even a single code word or a series of them in a row, we're going to lose more than one layer 2 Ethernet frame or layer 3 packet, which means that will cause transmissions in the network, which means that will increase latency. And if we increase latency in an AI network, we could see that we may have disrupted the learning process, for example. So that would cost a lot of time and money for people, which is why all this concern about performance of the interconnects and how important it is. Now, the other thing we have to do is look for our FEC margin, which I'll show examples, to allow room for bursty errors and still not have an uncorrectable FEC code word, which means our FEC overhead and our FEC margin have to be sufficient so that when bursty errors occur, which they will eventually occur, when they do occur, that they do not drag us into the greater than 15 symbol errors per code word area where we get an uncorrectable and therefore lost Ethernet frames or IP packets. So that's very important concepts to have in the test plan. Now, what else do we do? I talked about system level testing earlier, and what I mean is testing that interconnect exactly as it's going to be used in the network that is targeted for, which means we have to conduct long duration tests while analyzing the forward error correction performance, while looking at all of the layer 2 frame statistics and making sure that we are getting 100% throughput on the traffic, that we have a good FEC margin, a good FEC overhead, a good FEC margin. We want to test our interconnects for reliability as a standalone when possible, in back-to-back with fiber spools in the case of optics that have to traverse long distances like 500 meters to 2 kilometers, maybe 10 kilometers, maybe 6 kilometers, whatever the application calls for, we should test that application. And then, of course, as we mentioned, connect it to switches of different vendors. We want to look at use our FEC scrambled idle traffic. We want to do stressful layer 2 traffic. Now, we could have a webinar just based on that row. But however, today I just want to get the ideas across so that all of us are on the same page here. And then, of course, we talk about network deployment readiness. So I mentioned several times, and we'll probably mention some more, we want to keep testing these interconnects as if used in a real network under stress and in live production conditions whenever possible. And then we have to understand that even though we recommend testing the device or the interconnect as a standalone, if you only test it as a standalone, it does not guarantee its performance in many different network equipment systems. So we are strongly recommending multi-vendor interoperability testing. And we're starting to see the recognition of this by the high attendance at some of our recent MSA Plugfest, like the LPO MSA Plugfest that Keysight has been hosting for the last year and a half or so. We're continuing to do that to build the ecosystem and to educate people as much as possible on what we can do to help them get their testing done, but also recognizing how important it is to do interoperability testing between different vendors' equipments. And then we want to do the same thing with those interconnects, not only unto themselves and within different interconnects from different manufacturers. We also want to do the same thing for different manufacturers of network devices and equipment. Now, as I mentioned, we look at some key measurements to make this task easier. So in our blue braces at the top of the statistics chart on the right, we see our frame loss ratio value, we see the prefect BER, and we see the maximum symbol error per code word. In the red braces, we see the FEC overhead, how many symbol errors, how many FEC code words were transmitted with 0 errors, with 1 error, with 2 errors, with 3 errors, and so on, down through the distribution all the way to 15. That's our red braces. And you will see that they're slightly different. So our FEC overhead is often quite different, all right, when we take a look at this. Now, what you're seeing is two 800 gig optics set into 2 by 400 gig E mode. So we get 4 logical 400 gig E ports. So you're seeing 4 ports being compared. And you will notice, for example, their prefect BER is very different. Port 1.1 is to the -8. Port 2.1 is to the -10. Port 3.1 is to the -8. Port 4 is to the -9. And you might say, well, gosh, that sounds terrible, right? But actually, this is quite normal to see a different prefect bit error ratio per group of lanes, in this case, 400 gig lanes, or, a group of lanes to support 400 gig E. Or if we had a single lane, suppose we were in 8 by 100 gig E mode, we would see 8 lanes and we would see 8 of these important measurements. Now, so we look at our FEC overheads and we see they're also different. And you would expect that, right, to a certain degree. They will never be exactly the same. It is very unusual to see them the same. I have seen it. It does happen. And there are some cases where everything is working extremely well. And the important one, though, is the FEC margin, which is our green braces. Notice they are also, that margin starts in different locations. Our first port, it starts at FEC code words with 5 errors. Our second port starts with 3 errors. Our third port starts with 4 errors. Our fourth port starts with 5 errors. This is the margin where if we were to receive bursty errors under whatever conditions we're testing, this is the place they're going to show up, hopefully. And hopefully those bursty errors do not go beyond 15 symbol errors per code word and cause an uncorrectable event. So this is what we call the FEC margin. And for different types of interconnects, for different applications, these values are considered by customers to be different. And for different network applications, we might see different performance requirements. There's no single performance requirement. We can say that the standard did give us a performance requirement, but as I mentioned, every end user wants much higher performance than what we have in the standards. Okay, let's look at our solutions. Today, Keysight is shipping a 1.6 terabit Ethernet test system. We've shipped to many companies, dozens and dozens of systems. And these are all capable of 1 by 1600 gig, 2 by 800 gig, 4 by 400 gig, 8 by 200 gig. And they are 802.3 DJ IEEE draft spec compliant. In this case, we're showing some transceivers that are 2 by DR4. So we're really showing 2 by 800 gig in a bidirectional measurement. In this particular demonstration, however, we ran these transceivers at 1.6 T, meaning we ran 1.6 T MAC behind these host ports and ran that bidirectionally. So we have working systems, and we're one of the few vendors that are able to do that. There's a press release if you're interested in finding out more about this particular tester called the Internet and Network Performance Tester. We have two different types of hardware. We have a benchtop, which is office quiet, has a handle, only weighs 22 pounds, needs a single power cord with a 15 amp service. So it's meant to be able to be moved very easily. And we have a half rack system, which sits on a 19-inch rack mount shelf and has 2 ports per half rack. And you can get 2 of these half racks in a single shelf for 4 ports of 1.6 T in a 2RU rack mount. They all have common layer 1, layer 1.5, which we call lovingly PCS and FEC layer, where we look at the PCS statistics, the FEC stats, as we mentioned, and the FEC error distribution. And then we have our traditional layer 2, 3. And we recommend the benchtop if you're doing a lot of interconnect and CMOS work and you have what we call a high touch application where you're constantly inserting interconnects into the device and withdrawing them and so on and changing to different types and doing a lot of CMOS work potentially. And then if you're doing some switch and router performance, you can do that with the benchtop, specifically in a snake test as an example. And if you actually need network protocol emulation for those switches or routers, we also offer that on our benchtop. So you can do from layer 1 to full layer 3, including internetworking and networking protocol emulation on these platforms. We believe that the half rack is best suited for fully loaded applications where you load up all the interconnects and load up all your ports and connect them to your device center test, and you do rack mount based testing, a lot of regression testing, as well as high port count, high scale testing. We recommend our rack mount system. And one of the big differences is the rack mount supports optics up to 33 watts, air cooled up to 33 watts, and air cooled in the benchtop up to 40 watts, which is a big deal because some of these new 1.6 terabit optics, they start at 30 watts or more. So this is why I mentioned earlier this move in the long term to water cooled optical systems, because at some point air cooling is just going to run out. However, we've been quite innovative in getting these platforms to reach these levels in an air-cooled system that's quiet and does not require a lot of power to run them. So we have quite a bit of capability, and it's not just limited to only doing interconnects or only doing layer 1, digital layer 1 or layer 1.5. You can go all the way to full-blown network testing. Now, we have developed a new software called Interconnect Test System. And the Interconnect Test System helps you improve productivity in qualifying the interconnects. Now, if you look on the left, if any of this sounds familiar to you, then I believe you'll be strongly interested in our new Interconnect Test System software, just called ITS. ITS software is designed from square one. This is a brand new software, and it's targeted for interconnect testing, and it addresses all of these issues over here on the left. And if you're still chuckling from this list, because we go through this ourselves in our own optics and cables and interconnect testing and qualification, along with our many customers who do this, we're doing the same thing. And at this point, we felt that new software with new capabilities, including patented capabilities, was required. Now, you might say, well, what does it do for me? Well, we have a fast and easy user interface. Everyone says that. This one proves it. Basically, within 3 clicks in that software, you can do anything that that software is capable of doing in a browser interface. It's designed to validate error performance, functionality and error performance. That's what its sole purpose is for Interconnects. You can also, eventually we'll be able to do some switch testing, but right now it's focused on Interconnects. You can qualify 100 gig PAM4 to 1600 gig PAM4 Interconnects. So it's meant to support 800, what we call the 800 gig and the 1600 gig speeds. It does BER infect performance on all lanes with all the statistics that we just talked about previously. And it has a unique patented feature called the Interconnect library. The Interconnect library organizes the interconnect data and allows you to save it, recall it, use it, report on it, use it for new tests, and be able to track what you have done, not only in CMIS, but your test results and the configuration of the interconnect with that CMIS image and with those test results. So the library allows you to also add interconnects on your own. You no longer need to rely on Keysight to give you a new software version that supports the next interconnect. You can do it yourself. And you can reuse and compare interconnects. So you can compare the CMIS image between 2 different interconnects and find the differences on the whole image. You can compare CMIS configs. You can take a look and create something called playlists. So with our interconnect library records, we can take them, organize a test, then take them and put them into a specialized type of scheduler where you can create your own playlist and create the ability to run a test suite that's designed to be used with that interconnect. And then the last and very important thing is it automatically creates pass-fail reports to your tolerances, and it has a script generation capability. So if you create a test in the GUI, it will give you the REST API script automatically with the Python language interface. So you now can create test scripts without doing any programming. I'm going to turn it over now to Angela for a demonstration of the Interconnect test system software and the Interconnect library. Take it away, Angela.
Hello, everyone. And thank you very much, Charles, for your kind introduction. Let me quickly show you a demo of Interconnect Test System Software version 1. What we have here is the dashboard that you were taken to as soon as you access the software. And at the top portion of the screen, you can see a section that gives you an overview of what is happening with your chassis. So what users are playing with it, what ports you have, what interconnects are plugged into these ports, and their manufacturer, model, serial number, information about their type, as well as live temperature data. Okay, you can very easily go drill down into any of this, and you will be taken to live statistics for each of these ports, and you will be able to very, very easily and quickly change all of the settings that you have on the port. What you also have available is CMIS information, and you can see that the CMIS information is fully decoded. Instead of hex or binary data, you have user-readable strings. So in this case, the interconnect that I have here is using CMIS version 5.2, and I have OSFP 8X module identifier. And if I try to change any of the registries, all of the available options are fully decoded, so I can be safe in picking the correct one without bothering to understand the hex values myself. Okay, I'm not going to overwrite this particular registry, but I am going to show you the digital optical monitoring section where you have, again, live data. You can see the power readings changing live as we speak. And of course, the alarms are going to be, if the alarms are triggered, you're going to have fancy highlighting in this UI, and you can very, very quickly and easily change between ports. In this case, I have a passive copper cable, so there is no data available here. But if I go to port 4, I will see live data again, and the power outputs changing on the fly. I also see that I have a different CMIS version. And in this case, I see that the port is in FEC mode, and I can go check out the FEC stats. And I have some nice FEC tails here. There's also a handy checkbox in case I want to compare statistics across all ports. I just toggle this, and I have the information at my fingertips. Now, if I go back to the dashboard, in this lower section, we have results. Those are tied into the automated testing, and I have Interconnect library section. Let's quickly drill down into this. If I go on one of the interconnects, I see that there are 5 of them, even though I only have 4 ports. That's because what this does is build up a library of interconnects as I have plugged them into the chassis. So the first time I plug in an interconnect, I get an initial CMIS snapshot. And then as I use the interconnect in tests, I get additional CMIS snapshots that I can drill down into. And I see exactly what tests the snapshots were taken by, who ran them, and what the test result was in each case. I also have a handy link to see the actual test results that this particular interconnect was involved in. And if I go to, let's say, this particular interconnect, serial number 1, I see that I have this oops to debug tag here. And let's quickly drill down. If I do this, it's going to load up the test that was run. And this is my execution log for the test. And you can see a lot of nicely formatted information in a textual mode that lists exactly what was happening in the test, what statistics values were found for each iteration, and what the results were. We also have some very handy graphs for each of the ports. I can see the threshold very clearly mapped out, as well as the per lane statistics. And I can see that these lanes had a bit of a problem at some of the iterations. Okay, let me look at the settings. So I was using PRBS 23Q, and I had laser on off to do the link flap, and these were my tab settings in each case. Maybe I want to investigate this a little later. I can download the logs, or I can generate a PDF report. And here there are templates. I have a summary template that is by default selected. I can also have a detailed PDF report that includes a lot more information. This might be a little overwhelming. I can also go in and select any pages and registers that I want manually in order to customize my report further. Let's try to start with the summary report for now. Okay, I'm going to click on Generate Report, and it's going to have to wait for a moment because the report is being generated as we speak. Okay, so I downloaded it. Let me open it up in a new tab, and let's quickly look. So I can see who ran the test, what the test was named, when it happened, how long it took, and the overall result that's failed. I can also see what interconnects were involved in this particular test, and I can see a more detailed status. So it looks like the ports 1, 2, and 3 passed all 10 iterations, but port 4 was kind of undecided about whether it was going to pass or not. I have all the test and port settings handy, so I know exactly what was configured when I ran the test. And then I have the per lane results. And port 4, all lanes failed, damn. And we also have the handy charts that compare exactly what happened on each lane with the threshold, and I can definitely see that there were some big outliers for port 4. Okay, another interesting thing that I can do is I can just schedule a new run, and this is going to rerun the current test, or I can export the test. And what this will do is it'll give me a zip file, and I will very, very quickly go over here and unzip this. Okay, let me do that very fast. So what I have here is a README file. This one explains exactly what is happening. I have a requirements text. This is used to install all the Python packages that we need to run the test. And then I have this Python script that is the actual script that was used to run the test. The test configuration is separate. It's in the JSON file that we just saw here. And what happens in this case is that you can very easily change the configuration of any port or what ports are being involved or any of the test settings really without being afraid that you will affect the logic in the test. So if you want to change the logic of the test, you change the Python script. If you just want to change the configuration that you give to the test, you change the JSON file. So very handy, very easy to do your own automation whenever you want. Okay, I'm going to schedule a new run just to show you that it does run live. And then that is going to be it for the demo. Thank you very much, Charles. Back to you.
Well, thank you, Angela, for that excellent demonstration of the new Interconnect test system software. I wanted to provide a little bit of a look ahead into calendar year 2026. Keysight is introducing new error performance validation systems that will impact multiple areas of the interconnect development process. Early prototyping of interconnects, pilot and volume manufacturing where we do in-process or near-process inspections and measurements, and final product error performance validation. These are products specifically designed for the task and will help, along with the Interconnect test system software, to make your life easier in managing and automating the tests involving interconnects. And then these new products initially will address 1.6 terabit, 212G electrical lanes, and they have an eye towards 3.2 terabit and 448 as well. And we also have systems that include ultra high density applications for those AI network racks that we talked a little bit about in the technology area. We have solutions to address those as well, so talk to us about that. And I would like you to stay tuned for more news about these new products. And at this point, I'd like to turn this over to Barb for our Q&A and closing remarks.
Thank you, Charles, for that insightful presentation. Before we move into our Q&A, we'd like to take a quick poll to help us understand your level of interest in learning more. If you prefer not to be contacted, simply skip the question. You'll see 3 options on your screen, so go ahead if you choose to and make your selection, and then be sure to click Submit. Keysight hosts many free virtual events throughout the year, and we'd appreciate it if you could take a moment to complete the short survey that will also appear on your screen. Your feedback really helps us to improve future sessions. Now, let's dive into a few of your questions. If you haven't already, you can go ahead and type your question into the Q&A panel at any time. Charles, let's start with our first question. Let me take a look. We've got a few good ones here. Why don't industry standards focus on performance of the interconnect?
Well, Barb, that's a great question. And in fact, I have people asking Keysight this. Generally, and it's difficult to describe, standards revolve around architectures and electrical measurements and essentially create an environment that when we define a product like an interconnect or a silicon chip or something that goes into an interconnect, that someone can build it knowing if they build it with these architectural elements in place, it will work. Now, the other thing that standards do is they try to be all inclusive. So we want every company, when we build a standard, we want every company to participate that possibly can. And so therefore, the measurements, the maximum worst cases, the minimum worst cases, the thresholds for performance are set to the very worst case performance that everyone can still build the product at the lowest cost possible and have it be operational in a network. So what's changed today is that particular part of the standard and achieving that goal where everybody can play, as they say, has been achieved. But what's happened is the requirements have changed relative to these AI network infrastructures. And because of that, there are influences that require the interconnects to perform at much higher levels, several orders of magnitude better than as defined by the standards. So it's application requirements that are driving it, not necessarily definition of what an interconnect is.
Okay, that makes sense. Thanks.
Welcome.
Here's another. We've been measuring with simple BER systems for years. So why do we now have to evaluate interconnect performance using FEC or FEC?
Yeah, another great question. Forward error correction, FEC, has been around now since, let's just say, in the industry in general, as a measurement requirement, since sometime around 2016, 2017. You might say to yourself, well, hey, it's been 7 or 8 years. Don't we get this yet? Well, so with the advent of PAM4 signaling and forward error correction techniques, which is a transmit technology, forward error correction corrects bit errors before they show up on the line. So the idea of forward error correction allows these higher speed lanes. So our gigabits per second per electrical lane or optical lane, they have gone from 53 gigabits to 106 gigabits to 212 gigabits as we have today. As the lane speeds go faster, the need to correct is greater. So the need to measure the error performance correction has become greater. So if we're going to correct a whole lot of errors, are we correcting them correctly? Are we correcting enough of them? Are we correcting enough of these errors so that when there's an event in a network infrastructure, like a burst of errors, which is the nature of PAM4 signaling and the use of forward error correction and the algorithms that all support that, when a burst of errors happen, do I have enough margin? Do I have enough margin in my forward error correction process to accept some unpredictable errors that can occur at any given moment and still not have my Ethernet link go down, for example? So if we can measure the symbol error correction performance of the forward error correction process that involves our interconnect, then we can see how much margin we have. And we can actually, if we test long enough, we will eventually see these bursty errors, and we will see if they're enough to bring a link down or to keep that link up in the worst conditions.
Great. That's a really good answer. Thanks even for somebody not as technical as me. Thank you, Charles. Here's a 2-part question. Why is testing CMIS so important today, and how does it impact my test plan?
Yes. CMIS is a very large specification.
And for somebody, I forgot, I know what it stands for, but I forgot. Could you?
Common Management Interface Specification.
That's right. Yes.
So it's essentially the programming requirements for the interconnect. What kind of, who made it, serial numbers, part numbers, all of these different things go into the transceiver, all of the values for the lasers and the electrical properties, and just hundreds of values are programmed into these transceivers. But at the system level test requirements, let's call it environment, We have many different Ethernet configurations. So Ethernet speeds, there are many speeds. One optical transceiver could support 4, 5, 6, or 7 different Ethernet modes. One coherent optical transceiver could support multiple Ethernet modes plus DWDM gigabits per second per lane modes. So with all of these configurations, if we're going to sell that product to our customer, we have to be able to verify that every configuration works. And the forward error correction engines that are used are often different between different Ethernet speeds and different lane speeds that drive the Ethernet. So since there are differences between speeds and there are many different configurations, one we have to see, does the transceiver respond to commands to be changed for that configuration? And once changed, does that configuration work with the expected level of performance, error correction performance? And if there's 7 configurations, in the past there'd be 1 configuration, we'd have to run 1 test. Now there are 7 configurations for the same device and we have to run 7 tests. That's a very simple way of saying there's a lot more testing.
So when you're saying, so that second part of that question for the why testing CMIS is important. So you're saying it impacts their test plan because they have to run a lot more tests and
they have to run a lot more
bandwidth, less
configurations.
productivity kind of thing?
Yes. They have to run a lot more tests over different degrees of bandwidth speeds, and they have to run many different configurations in order to figure out, did I program this device correctly? And if I tell it to be one speed versus another, or this configuration versus that configuration, does it operate the way I believe it should as it was programmed? Yeah. Okay. So it's essentially a very big validation and verification process. Okay. And it's complicated and it requires skilled individuals to do it.
Perfect. Okay. Looks like we got one quick minute maybe here for one more question. What other new technology trends are impacting how we're testing interconnects?
Well, one of the most important, I think, is with the CMIS specification, there are new reporting. So, for example, the silicon that goes into the optical transceivers is intelligent, very intelligent, and it can actually calculate its own measurements, its own bit error ratio measurements. It can calculate laser power reception. It can calculate laser transmit power. So if we take a look at the advantages of using CMIS, there are measurements, there are all kinds of attributes and performances of different characteristics of the optical transceiver or the copper cable that we can look at now, but yet that presents a whole nother set of things that have to be looked at.
So CMIS is actually a trend then that you're talking. So like
are they implementation of CMIS has become an industry standard, ubiquitous industry standard with a high degree of complexity, and more content is being added to it as we go into faster lane speeds, a broader set of optical transceivers and how they work and how they're configured. It's become a very broad set of offerings out there, and CMIS has to manage them all, and therefore it's a very big task for us to test all these different configurations.
Okay, and obviously AI is probably playing a big role in all these things too, in the higher speeds.
Absolutely. With AI, the link reliability, meaning we cannot have links go down in the network during a large language model training process, for example. That just cannot happen. And if it happens, sometimes 3 or 4 or 5 days of learning has to be restarted, or it has to be redone in some way, which costs time and money on very expensive networks that require tremendous amounts of power and facility support. So it's very expensive to have to redo your work. So reliable interconnects just means that the network infrastructure is not going to be the problem when it comes to creating services related to what AI delivers. In other words, creating the network service that provides the information that AI calculates for us.
Gotcha. Great. Well, it looks like we're out of time. That's all the time we've got for questions today. I really appreciate it. We will follow up with the rest of your questions that you've sent in. We'll get back to those via email. And as we wrap up today's presentation, remember that we will also email you a link when the on-demand version is available, along with a copy of the slides. And once again, thanks a lot to our presenters, Charles and Angela, and everyone online for joining us. This webinar was brought to you by Keysight Technologies. And if you'd like a list of upcoming future events, you can visit us at www.keysight.com/find/events. Thanks, and bye for now.
Thank you, Barb.
Thanks.